I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll understand derivative of exponential functions, starting from the very basics. We'll first review some concepts, then understand the derivative of f of x equals to b to the power of x. We'll investigate and then discuss the result. It is a very important video for all the IB students who have just started to learn about derivative of exponential functions. In case you want to learn from me, you can always send an email on the address given or contact us on the website.
After attending university. The winner of this year's Certificate of Achievement Schulich Leader Award is Akshi Kandilani.
Great. Our student Akshit gets highest marks and the most prestigious Schulich Leader Award. You can be there. Join our classes and excel.
Now let us first begin with the basic concepts. When we say derivative of exponential functions, we are basically working with the parent function, which is f of x equals to b to the power of x, where b is the base and x is the exponent, or you can say index or power. Now, do you remember the restrictions on b? Well, x could be any real number. Let me rewrite this. X belongs to real numbers. There are no restrictions. However, b has a lot of restrictions. So what about b? B has to be greater than 0, and also b, as you know, is not equal to 1. So can you tell me why b is not less than 0? Well, the exponential function's graph, if you sketch, will be kind of like this. And that is when b is greater than 1, right? And b is, let's write just that, b greater than 1. So it is growth. On the other hand, if the value of b is between 0 and 1, then the graph will be kind of like this. So this is when b is between 0 and 1. So let me write like this. So in either case, b is not equal to 1, right? Now the thing is, why b is not less than 1? Think about this. If b is, that means b is negative. Then what happens? Let's consider minus 2. So what is the power of minus 2? When I take this as 1, I get minus 2. And what is minus 2 to the power of 2? That is plus 4. And minus 2 to the power of 3 will again give it negative value. So do you see what is happening? If b is less than equal to 1, then the values are kind of going from positive to negative, negative to positive. We do not have a continuous function, right? Also, you can notice that in case b is equal to 1, then we have a straight line. Now, this straight line is for b equals to 1. There is no growth or decay in this particular case, and therefore, we do not consider b equals to 1 for exponential functions. So, I think that concept is clear to you. So we are basically defining a function and we are saying that it is greater than 0 base and it is not equal to 1. And I hope the reasons are absolutely clear. Perfect. Now with that in mind, let's focus on the derivative, which is the main objective. Now we'll find derivative of the function f of x equals to b to the power of x, where you know that b is greater than 0 and it's not equal to 1. Belongs to real numbers, of course. So we are going to use the basic definition, which is given to you right there, which is the derivative of any function can be found by difference quotient method. So limit h approaches 0, f of x plus h minus f of x over h. So that is the definition. So using the definition of derivatives, which is right there, we'll now find the derivative of our function b to the power of x. Since the function is b to the power of x, I can now write this as limit h approaches 0, b to the power of x plus h minus b to the power of x over h. Makes sense, right? Absolutely clear to you? Now, what is the meaning of b to the power of x plus h? That means it is product of b to the power of x and b to the power of h. So let's write like that. So we have limit h approaches 0, b to the power of x times b to the power of h minus b to the power of x over h. And you can see now we can factor out b to the power of x and rewrite the derivative as limit h approaches 0, b to the power of x is common. We are left with b to the power of h minus 1 over h. Now in this particular limit, you can see that b to the power of x is independent of h, right? So if h is approaching 0, it doesn't change the value of b to the power of x. It remains as it is. So we could factor this out, right? It is a very critical part of our derivation. You should understand why we have taken out b to the power of x outside, right? It could be a communication question in your test paper also. So we are left with b to the power of x, limit h approaches 0, for b to the power of h minus 1 over h. So can you tell me why did we take this out? Mainly because it is independent of h, right? So within the limit, only parameters affected by h have been included. Makes sense, right? Now the critical part of this derivative is to understand what is this? What is this limit b to the power of h minus 1 over h when h approaches 0? In the books, you all have seen what this is, and it's very clearly written as b to the power of x times this limit is f of f derivative of f at 0. Now that is sometimes not understood by many students, and that is the reason why they come to me many times with this particular question. How come we can go from this step to this step? It is absolutely correct step, but understanding is kind of difficult. So I'd like you to really think about this part. We have got the derivative, right? So we have the answer right there. We can say that if f of x is equal to b to the power of x, that means that the derivative of this particular function is basically b to the power of x. It means the value of the function at x, right? Times one constant. And this constant is the slope of the tangent at the y-intercept, where x is 0. You get the idea. So from this definition, we get a very important result, and that is to say, the derivative at any point on b to the power of x is the value of the function at that point times a constant, and this constant is slope at y-intercept, where x is 0. You get the idea. So, okay, this definition is clear, but now the question remains, how did we go from limit h approaches 0 of b to the power of h minus 1 over h as the derivative as y-intercept, where x is 0? Let's explore this a bit more, right? And then the derivative is there for you. We will further move ahead. So let's try to understand this, right? So we were saying that what is, after all, f prime 0? That is what we need to figure out. Now going back to the basic definition, which is there for you, right? Now in this case, if x is 0, then how the formula changes, right? You remember that? So let me rewrite the formula. So will be f of 0 plus h minus f of 0 over h, right? And of course, limit h approaches 0. So let me squeeze that in, right? So limit h approaches 0. Perfect. Now since our function is b to the power of x, we can write this as limit h approaches 0 for b to the power of 0 plus h, right? 0 plus h minus b to the power of 0 over h. Now, as you know, anything to the power of 0 is 1, right? Anything to the power of 0 is 1. So we know that b to the power of 0 basically is 1. So we can write this as what? So we could write this f prime at 0, which is the y-intercept, is limit h approaches 0, and that, is product of b to the power of 0 times b to the power of h minus b to the power of 0 over h. Now since b to the power of 0 is just 1, I could write this as limit h approaches 0, b to the power of h minus 1 over h. Makes sense? So you see that this particular part which we highlighted is indeed equal to f prime 0, right? So we'll summarize this as the derivative at 0 is indeed equal to limit h approaches 0 of b to the power of h minus 1 over h. Make sense? So let's get back to this. So that is what we proved just now, right? That is what we just proved. Well, alternate way to look into this is very clear. If you have this particular expression, and if you want f prime 0, just substitute 0 here. You get b to the power of 0, which is 1, and we get this expression as such, which should be equal to f prime 0. Perfect. So I think this is absolutely clear. Now let's understand this particular part. Now what we are saying is that if we have an exponential function, which, let me just sketch b to the power of x, then what you need to figure out is the slope at the y-intercept, this particular slope. You see that at y-intercept. So this slope is what we are saying, f prime 0. Correct? And the graph is of b to the power of x. Now if I want derivative at any point, in that case, it is value of this function. For example, if I take this point as, let us say, if I take this point as 7, let's say, x value 7, then this will be b to the power of 7, correct? In that case, the derivative of this particular function at 7 will be what? It will be the value at 7 times the derivative at 0, means this derivative, f prime 0. You get the idea. So that is how you could get the derivative. That's what it means. Let's get back to our derivative itself now. So you have clearly understood what this derivative is. So now let's further explore the derivative which we have, that if the function f of x is equal to b to the power of x, in that case the derivative is indeed b to the power of x times the derivative at 0. Now here, derivative at 0 is a constant, right? So what are these two things? So this term here is value of function. At x, right? B to the power of x. And what is this? This is a constant. Slope of tangent at y-intercept. Because at y-intercept, we have x equals to 0, right? So that is a constant at y-intercept. It really means that we have come out with a very interesting result, that the derivative of exponential function is the value of the function times this constant. Perfect. So now, what we could do is we could explore different values of b. What I'm trying to say is you can find what is the derivative of the function where f of x is 2 to the power of x, let's say, right? So we could do 2 to the power of x, we could do 3 to the power of x. We can explore these derivatives and find what are their rate of change at 0. That is to say, for 2 to the power of x, let's sketch a graph and then see what we're trying to say. Let us say if the graph of 2 to the power of x is kind of like this, this is, let's say, 2 to the power of x, and then let me sketch a graph of 3 to the power of x. So 3 to the power of x, both will go through the same y-intercept, but here it is much lower values, and here like this. So this becomes 3 to the power of x, and the earlier one is 2 to the power of x. Now in both cases, we know that the constant by which this is multiplied is the slope of tangent at x equals to 0, right? So let's draw that. So for 2 to the power of x, this is the slope of tangent, right? This is for 2 to the power of s. So this value we should calculate. And the other value which we have is at 3 to the power of x, and which is this, right? So this is the slope of the tangent. Now, you should evaluate this. Once you evaluate this, you'll figure out that this tangent is around 0.69 something. That is the slope. And here, the slope is 1 point something, right? So it is slightly higher than 1. So what we notice is the tangents are, for 2, it is less than 1, and for 3, it is greater than 1. Slope of tangent. So that means there should be some number in between where the derivative at 0 is equal to 1. And that number for which the derivative of 0 is 1 is actually e. Perfect. So that is what we have. So let's first try to understand where we are. So we started with the derivative definition and found from the definition itself that for b to the power of x, the derivative of the function indeed is b to the power of x times f prime 0, where f prime 0 is this part, right? So if the function is b to the power of x, then the derivative is the value of the function times the constant, which is slope of the tangent at 0. So that becomes our general expression for any exponential function. In words, we can say that the derivative at 0 is a constant and f of x is the value of the function, right? At x equals to 0, of course. The derivative at any point is the product of value of the function at that point and a constant, which is f prime 0. Perfect. So I hope you have understood this part. What we need to do really is to investigate f prime 0. When is it less than 1? When it is greater than 1? And can we have a value which gives exactly 1 as f prime 0? You get the idea. So that is what we are going to explore now. So how do we explore this? We'll use difference quotient method to explore, right? So basically, to find what is the derivative at 0, we'll again use the same basic definition, right? And in that case, what we have is this particular value. So let us take a small value of h. So let h be equals to 0.001, right? So if I take h is 0.001, which is significantly less than 1, we can derive at the results for 2 to the power of x. I mean, for different values of b to the power of x, as b of x could be 1, 2, 3. And then we have a special number e, correct? So if you do this calculation, what will you figure out? Here the calculations are done for you. So you should actually try them out. So we did it for h equals to 0.001, and definitely the value of slope of tangent at 0, which is defined as b to the power of h minus 1 over h for different values of b. Well, of course, if I write b as 1, then this value is 0. That's a horizontal line. Well, b should not be 1, but we just took it for interest. But as we increase at b equals to 2, we find that the value is 0.693, less than 1, I mean. But when b is 3, this point 1.09 is more than 1. And therefore, in between, we should get the exact value. And for that, we tried this number e, which gives you exactly 1. That's the Euler's number, right? In one of our videos, we have found the value of e, and that value of e, when you put, you get this. So significance of Euler's number is that slope of tangent at any point is the same as the value of the function, since the derivative itself is 1, right? So we can now summarize our result for the derivative, which we have just done. Derivative of the function f of x, where f of x is b to the power of x, and b is greater than 0 but not equal to 1, is given by the value of the function times the derivative at the y-intercept, which is a constant. And we figure it out that for 2 to the power of x, that slope of tangent is 0.0693. For 3 to the power of x, it is 1.09867. And in between, we get the value when it is e. So if the function is e to the power of x, derivative is exactly e to the power of x. Perfect. So that is where we are going to end this particular lesson. In our previous video, we did explore and found the value of e. Now here is the result of that. So in our earlier video, we have found the value of e. E is defined as limit 1 plus x to the power of 1 over x. And when we approach from plus and minus of 0 sides, we approach a value whose significant figures 2.718. We found it accurate to 1000 is 2.718, right? So you could put e, and that is how you can continue here and find more accurate result of e. Perfect. So let's get back to our situation. So we have this particular rule, and let me now summarize that if the function f of x is equal to e to the power of x In that case, the derivative of the function is e to the power of x. However, if the function f of x is something else, base is not e but something else, then the derivative of the function is the value of the function times the slope of tangent at y-intercept where x is equal to 0. So that becomes the derivative of your exponential function. So I hope with this it's absolutely clear how do we derive at this result from the basic first principle, the definition of derivatives. Perfect. So I hope this is absolutely clear. Feel free to write your comment, share your views. In case you have any suggestions or doubts, you can always send an email on the address given. You can also contact us to learn and explore calculus. Thanks for your time and all the best.